Heteroskedasticity does not cause bias or inconsistency in the OLS estimators of the coefficient beta. When the first four Gauss-Markov assumptions hold, the OLS estimates are unbiased and consistent. It has nothing to do with the structure of the variance of the error term. Second, the goodness of fit measure R squared is not affected by heteroskedasticity. By its definition, R squared equals the explained sum of squares divided by the total sum of squares, or 1 minus the ratio of the residual sum of squares to the total sum of squares. The three sums of squares are unaffected by heteroskedasticity. Third, the OLS estimates may not be efficient in the presence of heteroskedasticity. That is, the OLS estimator may not have the smallest variance among all linear and unbiased estimators if the error term is heteroskedastic. For instance, if the variance of the error term is a linear function of the explanatory variable, the weighted least squares WLS estimator may have a smaller variance than the ordinary least squares OLS estimator. Only when the error term has a constant variance, along with the other four Gauss-Markov assumptions, the OLS estimators have the smallest variance among all linear unbiased estimators. When heteroskedasticity is present, OLS estimates may not have the smallest variance among all linear and unbiased estimates. Fourth, the statistical inference may be misleading if the error term is heteroskedastic. The variance of beta hat is based on homoskedasticity. It will be biased without the homoskedasticity assumption. As a consequence, the standard error of beta hat will no longer be valid for constructing confidence intervals and t-statistics. The usual t-statistic does not have the t-distribution. It leads to an invalid t-test. The statistics we used to test hypotheses under the Gauss-Markov assumptions are not valid in the presence of heteroskedasticity.